Using one single pin to control a single LED is fine, but what if there are many LEDs in your project to deal with? Spending a pin for every single LED is not a solution in this case, right? Today in this video, I'm going to use PCF8574 Pin Expander to control 8 LEDs to form a sound level indicator using only 2 pins, which are required to interface the pin expander over I2C using STM32 microcontroller. We are going to build our own sound level indicator from scratch today, so without any further ado, let's start our video. Alright, so let's start with our hardware connection. At the first look, our circuit diagram may seem a little bit big, but it's fine. It's quite easy to understand, so don't get scared. First of all, the I2C bus, serial data and serial clock lines are connected to the PCF8574 pin extender, and they are pulled up to 3.3 volt via 10 kilo ohm resistors, which is I2C standard. A0, A1, A2 pins are I2C slave address determining pins. We will be talking about that topic in details in just a minute. And lastly, P0, P1 till P7 pins are the output pins of the pin extender. They can be used as input as well, depending on the I2C packet transmitted by the MCU. But in our application, they will be used as outputs. So in short, the working principle of the PCF8574 integrated circuit is that it receives the data over I2C in serial manner and outputs it in a parallel manner over P0, P1 till P7 pins. And that's it, just as easy as that. So let's get to STM32 MCU and start its configuration.
Alright, so let's start with our MCU configuration. As you may have noticed, I switched to dark mode, so I advise you guys to get used to it. As you can see here, I've enabled I2C1 driver. So let's have a look at its configuration. The I2C driver is enabled from here, as you can see. Actually, we don't need to modify anything inside this configuration. The I2C clock speed will stay as it is, 100 kHz. Because this is stated in the IC datasheet, and we see this piece of information just over here. The IC that we are going to interface is PCF8574, and it requires a voltage between 2.5 to 6 volt, so it can run with 3.3 volt, which is the voltage required to run STM32 microcontroller that I'm using currently. I'm not going to use the interrupt pin of the PCF8574 IC because the application that I'm going to implement is based on extending the number of the output pins, so this won't serve my purpose. This actually can become quite handy when interfacing buttons to form some sort of a keyboard, so we may consider that in some other application. Let's get back to our STM32 Cube IDE and start coding. So if you have been watching the series that I've been working on, the electronic piano series, you will notice that the code have been modified a little bit. I worked on organizing the whole code to make it more readable so you guys can import it to your code and work on it. So if you are new here, it's fine. This tutorial will be dedicated only for implementing the necessary code used to interface the LED indicator that we are going to use today, which is using PCF7574 Pin Extender. So let's carry on. So first of all, an indicator handler is initialized here, and inside the handler there are several variables that are going to be used to interface the indicator. The ones that I'm using currently in my software are indicator enable to decide when to start I2C transmission, indicator LED set to decide whether we are turning on a new LED or turning off an LED, indicator buffer. This is the buffer that is going to be transmitted over I2C bus. It will be carrying the information that the pin expander will be outputting in a parallel manner. So let's have an example and see how this PCF7584 pin expander works. So here, suppose that a data of 5 hex is being transmitted from an MCU, STM32 in our case, transmitted over I2C bus to PCF8574 pin extender.
And once the data is received to this IC, it will be outputted this way. I2C slave address should also take place inside our handler, and we see that over here. This variable can become necessary if you are going to interface several ICs at the same time. But in my application, the value that's going to be stored inside this variable won't be changing. So let's have a look how the I2C slave address is determined. So we see here in the slave address byte, this part of the address is fixed and doesn't change. And this is the varying part of the slave address. It depends on the hardware connection and on the operation that we are going to do. A0, A1, A2 are pins in the IC hardware, and connecting them whether to the ground or to the VCC will change the slave address. And the last bit will determine whether we are writing or reading from the IC. In our case, since we are using it as an output extender, this bit will be always 0. So let's get back to the IC pin out and see how we are supposed to connect the address pins to determine the slave address. And these three pins, A0, A1, A2, are used to determine the I2C slave address. This feature in I2C is quite handy when you are interfacing several slaves at the same time. But in our case, we are interfacing only one slave, so it's not that important. In our application, I will be connecting them to the ground, so the I2C slave address will be as follows. Alright, let's get back to our code and continue talking about our handler. So after the indicator address, we see the indicator counter. This indicator counter will carry the number of LEDs turned on by the output pin extender. And the difference between the indicator counter and the indicator buffer is that the indicator counter will carry the number of LEDs in integer form, while the indicator buffer will carry the data that will be transmitted to the pin extender, which will be bitwise. So, for example, if the indicator counter carries the value 3, which indicates that 3 LEDs are turned on, the indicator buffer will carry a value of 7, because it will mean that 3 bits are activated. And that's all. The rest of the variables that I did not mention will be used to add more features in the future to this code. So let's keep this for another time and get back to our main code and see how this handler will be used. There's one thing I want to do before carrying on. I want to make the font of the code larger so you guys can see while watching this video. So from appearance, I go to font, and then from the editor menu, we edit the font size. Let's make it 12. Let's see how it looks like. Yeah, I mean, this will be better. Yeah, I will leave it that way. So let's get back to our work and go to our main to see how things are going on. So first, inside the main, we see that the LED indicator handler is initialized here, and inside the while loop, we see the address of the handler is passed to this function where all the magic will take place. So let's get inside and see how things are going on. So as far as you may remember from my previous tutorial, I was working over a menu button with multiple functionalities. So what I implemented was, when the button is pressed once, the sound level is incremented one step. When the menu button is pressed twice, the sound level will be decreased one step. So here I'm going to use the LED indicator to give some information related to the sound level. When the menu button is pressed once, so I want to show that one more LED is turned on, indicating that the sound level has been increased one step. So this whole code will only be executed when the menu button is pressed, right? So what I want to say here is that this member of the handler is activated inside the main when the menu button is pressed. And it's checked here in order to take an action depending on the pressing manner. So let's see how the indicator handler is enabled inside the menu button handling functionality. Yes, here we are. So I'm going to go through this as fast as possible because this is the code of the previous tutorial. It still needs some organization. So here we see in one button click case, we see that the indicator is enabled and the counter is incremented once, and a new LED will be lightened up. A similar scenario goes in the menu button double click state. So the indicator is enabled again. The indicator counter is decremented in order to reset one LED. So having this information and this modification, our LED indicator handling function will have meaning. And let's see now how all this data is processed. So let's head back to the LED indicator handling part. So as you can see, this whole function operates only when the indicator is enabled by the menu button. And inside the if condition, we see that the LED indicator is disabled, so this piece of code is executed only once, and then the LED indicator buffer is filled inside this function. We see that this function takes the handler as a pointer, so whatever modification occurs here, the value stored inside the buffer will be changed as well. So first of all, before modifying the indicator buffer value, we are going to check the value that it carries currently. So if the number of the lightened up LEDs is 0 and the request of turning off an LED is passed to this function, we are going to reset the indicator buffer, so no LED is lightened up. Otherwise, we are going to either turn on a new LED or turn off an LED. And this process will happen by updating the value inside the indicator buffer. So here in these two lines of code, practically we are going to transfer the number of the LEDs that we are going to light up to load it to the indicator buffer. And this happens as follows. Say that we are going to light up the LED number 4. So the indicator counter will have the number 4, and then one bit is shifted 3 times to the left. And yeah, here we go. The 4th bit inside this variable is activated. And then this bit is used to set the respective bit in the indicator buffer using setBit macro, which is located in the STM32 F1 header. Keep in mind that adding up a new LED to the indicator buffer should not mess with the data stored previously inside the buffer. So that's why OR operation is used. The scenario in LED turn off request does not differ that much, because here the indicator counter will be decremented in the menu button handling function. So considering the same example, if we are going to turn off the 4th LED, the counter value will be decremented to 3 in the menu button function, and then one bit is shifted 3 times to clear that bit inside the indicator buffer. And yeah, from this point, our indicator buffer is ready to be transmitted over I2C. So let's get back to where this function is called. So here, after loading the indicator buffer with new data, the buffer data is passed to a temporary variable, and then the value inside it is inverted. This step is actually done because of the hardware connection that we were talking about at the beginning of the video. I've used this convention to make things easier to read, in a way that it doesn't affect the code walkthrough. So this is the actual thing that's going to be transmitted over I2C, and here the I2C master transmit function is called, with the address that we had determined before. And yeah, so now let's have a look at a complete I2C packet. So I used my logic analyzer to sample the data on the I2C bus, and here we see a complete packet sent by our MCU. We see the I2C slave address part and the data transmitted to the slave. So if we have a look at the address part of the packet, we notice that the transmission is done in write mode, and the rest of the bits are the slave address, just like the datasheet was recommending, with setting the A0, A1, A2 to 0, which is done by the hardware. The other thing to notice here in the data part is that the data is sent inverted. So here the actual data is 7 hex, because we are lighting 3 LEDs. And this is of course done because of the hardware connection, as I've mentioned before. So now let's have a look at the actual LED indicator in reality and play with it. So here we see the PCF8574 Pin Expander. I've constructed it this way on a breadboard. So I've done it this way so the pin out starts in order. So this is P0, P1, P2, and it goes until P7. So we have 8 output pins in total. And in this part we see the I2C slave address determining pins, and they are all connected to ground. And the I2C lines, the data and the clock lines, are pulled up to 3.3 volt via 10 kilo ohm resistors. And under this cover there are 8 LEDs connected to the pin extender via resistors. The anode of the LEDs are connected to 3.3 volt, and the LED cathodes are connected to the resistors. So the plastic cover is this one. I've printed it on my 3D printer. I will be sharing its STL file in the GitHub repository. So it works that way. Let's energize the board and see how it goes. So let me turn off the light so I can see better. So everything is working now just like we have implemented in our code. And I will be sharing everything related to this video in the GitHub repository shared in the YouTube video description. And now let's activate the sound level test. Alright, thank you chicken, but that was not the test that I meant. So now we see that the indicator has meaning in our application, and it's quite useful actually. Alright, this brings me to the end of this tutorial. If you have learned something new, please subscribe to this channel and let your friends know about useful electronics. And you may consider supporting me on Patreon to keep such videos coming. Stay tuned and bye bye.